So let's take a look at this clean graph. I'm going to set up my axes. Here's my x-axis, my y-axis, and my z-axis. First, I'm going to draw my mountaintop. I know that in the xy plane it has a circle of radius 4. And in the yz plane we have this downward facing parabola. So that's sort of the look of my mountaintop. Now let's go ahead and add in the elliptical path. We knew the elliptical path had a major radius of 3 in the x direction and a minor radius of 1 in the y direction. So my circular path just in the xy plane would look something like this. But obviously, my probe actually isn't traveling down here in the middle of the mountain. It's traveling up on the surface of the mountain. And as it travels this elliptical path, it's going to be traveling up and down along the surface of the mountain. And if I were to sketch something that looks like, I know that the wide parts are going to be lower down on the mountain, and the narrow parts are going to be higher up on the mountain because the narrow parts have higher z values. And if I trace in these lines, I end up with a path that looks something right as I travel up and maybe down, around, that way. So as the probe travels along this path, it's going to go up and down along the curvy mountainside. My picture isn't perfect, but it gives us an idea of what's going on. And the question that we're asking is, as time changes, I want to know, as I have changes in time, what happens to the elevation of the probe? And I say two things are going to happen. And this is my sketch of what's going on. That a change in time means that I'm going to have both a change in the x direction and a change in the y direction, right? So a change in time gives me both a change in x and a change in y. And because of that change in x and change in y, that's going to result in a change in elevation due to the x change, and also a change in elevation due to the y change. So both the changes in x's and y's are going to impact the elevation of the probe. That's our motivating idea. And now we're going to actually solve this two different ways. So my first way is by direct substitution. Now that I have an idea of what my picture looks like, and I have an idea of what these changes are going to do to impact my change in elevation. So by direct substitution, I'm saying I want to know what is my change in height, meaning what is my change in this z value of my function? How am I moving along the surface of this function as time changes, as I move along this path? So really what I'm asking is, I want to know what is the derivative of my f function that's evaluated along my path c of t with respect to time. This is what I'm trying to find out, because f of c of t is exactly taking this green path and plugging it into my mountainside, and it's f of c of t is going to be this curvy path up here in 3 dimensions. And I want to know what's the derivative of the height of this curvy path with respect to time. So let's just take it step by step. F of c of t, that's a composition of these two functions, and I can go ahead and solve for that. So I'm going to give myself a little more space. F of c of t, I'm just taking my c of t function and plugging it into f. My c of t function is given by 3 cosine t sine t. And recall the way that this is written, and maybe I should write this up to remind us as well. This is saying that my 3 cosine t is my x component, and my sine t is my y component. So I'm going to take 3 cosine t and plug it into my x component, and sine t and plug it into my y component, and I end up with 16 minus 3 cosine t squared minus sine t squared. So this is the composition, and now I want to take the derivative of this with respect to t. So what happens when I take the derivative? We know how to take derivatives. My derivative of f of c of t with respect to t. The derivative of 16 is 0, it's just a constant. The derivative of this whole chunk I'm going to have to use chain rule because I have a composition of an inner function and an outer function. So the derivative of the outside is going to give me negative 2, 3 cosine t times the derivative of the inside, which in this case, the derivative of 3 cosine t is negative 3 sine t. Gosh, I ran out of space a little bit. And now the derivative of my second component, again I'm going to have to use chain rule, and I get minus, maybe I'll write it, I'll continue it down here, minus 2 sine t times the derivative of the inside function. The derivative of sine of t is cosine of t. And we can do a little bit of algebra to be able to simplify this. And I'm going to record our findings up here, up in the board, because it'll be interesting to compare it to what we'll find in a second using chain rule. So up here, we just found that the derivative of the composition f of c of t with respect to t is given by negative 2 times 3 times negative 3 becomes positive 18. Oh, positive 18 cosine t sine t minus 2 cosine t sine t, which gives us 16 cosine t sine t. I just simplified that using algebra. Let's check and make sure that I did that correctly. So I have minus 9 times negative 2 is positive 18 cosine sine minus 2. I agree. Hopefully you agree, viewers at home. So this is one way to think about doing this problem. The next way is to use our chain rule. So by chain rule, if I want to take the derivative of my f of c of t function with respect to t, one way I can think about doing this, just like we saw in our picture, this change in elevation, the change in my z-coordinate, is going to be dependent upon the changes of each of the x and the y coordinates individually. So I can represent this derivative as the derivative of my f function with respect to x times the derivative of x with respect to t. This is exactly like one-dimensional chain rule. If I just had a one-dimensional function, if this was just f of x, this would be chain rule and we would be done. But my f function isn't just a function of x, it's also a function of y. So I also need to add in my derivative with respect to y times the derivative of y with respect to t. Intuitively, this makes sense. It's just an extension of normal chain rule. What do all these symbols represent here? Let's talk through what this would mean computing by chain rule. So what is df dx? It's the derivative of my f function with respect to x, which in this case is an easy derivative. Treating y as a constant, I get negative 2x. What is dx dt, though? For this chunk, I need to look at my interior function, and I see that x is exactly equal to 3 cosine t. So if I take the derivative of 3 cosine t with respect to x, it's just going to be negative 3 sine t. So that takes care of the x component terms, or factors, sorry. And then looking in the y direction, my derivative of f with respect to y is negative 2y. And my derivative of y with respect to t is looking at this function where y is equal to sine of t. And so the derivative of y with respect to t is just going to be cosine t. And we're done. Almost. Here, we got our derivative with respect to t to be this simple-looking thing, whereas here I have a really complex-looking thing that has x's and y's and sines and cosines. For convention's sake, and actually clarity's sake, my derivative function was written all in terms of t, so I'm going to go ahead and plug in functions of t for each of my x's and y's, which is easy enough to do because I already know what x is equal to in terms of t. So this becomes, by plugging in x being equal to 3 cosine of t, I get negative 2 times 3 cosine t times negative 3 sine t. And then plugging in sine of t for y, I get minus 2 sine of t cosine t. Does this look familiar? It should look familiar because this is exactly the same operations that we did when we did the substitution directly. And what do we get? Notice that we get exactly the same thing. This is 18 cosine t sine t minus 2 cosine t sine t, which ends up being 16 cosine t sine t, which is exactly what we wanted. So we have seen multivariable chain rule. We computed the derivative directly with the composition function, and then we computed it using chain rule. Let's generalize this chain rule to see what it looks like for more than one variable. The book uses a really cumbersome notation. I don't think that I want to introduce the cumbersome notation. Instead, I'm going to look at a function where x is a function of three variables, s, t, and u, where y is a function of three variables, s, t, and u, and z is also a function of three variables, s, t, and u. It need not be the case that you could have, in the example we just saw, we just had x's and y's, and they were just a function of t by itself. But you could imagine x's, y's, z's, and w's all being functions of many, many more variables. And then let's say that f is our function of x, y, and z. And I want to know, what is chain rule for df ds? So this is the composition of my function f in terms of all of my x, y, and z terms. And it is, hopefully, exactly what you think it might be. You could think for a second. I'm going to have to take the derivative of f with respect to each of the major variables, x, y, and z, and then I'm going to have to multiply each of those by the derivative with respect to the minor variable, s. So that looks like df dx dx ds plus df dy dy ds plus df dz dz ds. And you can, in your mind, if I change this s to a t, one of the other minor variables, obviously all these s's would change into t's. So let's go ahead and see an example.